Okay, after knowing some facts about ionic bonding and covalent bonding, let's see how we can draw the Lewis dot formula for the covalent compounds. So let's start with Ch4 methane molecule. The first thing we need to do is to count the total number of valence electrons in the molecule. The number of valence electrons on each atom is the same as group number, or let's say the last digit in group number. So for example, if carbon is in group 14, we have one carbon and there are 4 valence electrons in it. Group 14, 4 electrons. Plus, you have 4 hydrogens times 1, so total valence electrons will be 8. Now, let's put the central atom in the center of the molecule. You have 4 hydrogens and 1 carbon. Keep it in mind that hydrogens can never be central atom. So you put your central atom. The next thing is to put the valence electrons around it, like complete its octet. What is octet? Octet rule says that except for hydrogen, the rest of the atoms will have 8 electrons around them. So let's put these 8 electrons around carbon. What other atoms do we have? 4 hydrogens. So put 4 hydrogens as well. Do we have any other valence electrons to show? No. We use all of these 8 electrons on carbon, so none left. That makes sense because hydrogens can never accept more than 2 electrons, and you have shown all of these valence electrons on the molecule. The next thing you do is, because these electrons are shared, you show them as single dashed lines as bonding electrons. In the next chapter, I'll show you how to draw the correct structure of the molecules using their exact bonding angles. But that's too early now, don't worry about it. So one more time, count the total number of valence electrons, determine the central atom, put the rest of the atoms around them after you complete the octet on the central atom. If there is any other electrons left, distribute them on the other atoms and change the bonding electrons to single dash lines. Ready for next example? Let's work on NH3. Total valence electrons. 1 nitrogen, it's in group 15, so 5 valence electrons. Plus 3 hydrogens times 1, 4 hydrogens, again 8 valence electrons. Nitrogen is your central atom. Go ahead and complete its octet and put 3 hydrogens. And change your bonding electrons to single dash lines. Any other electrons left? No, you use all of them are on nitrogen, so none left. And again, makes sense because hydrogens cannot get more than 2 electrons. In case of OF2, let's work it together. Oxygen is in group 16, so it has 6 electrons, 6 valence electrons, plus 2 fluorines. Fluorine atom has 7 valence electrons in it. So 2 times 7, 14 plus 6, 20 valence electrons, right? So let's draw it. Between the 2 atoms, you always choose the less electronegative element as central atom. For the previous examples, hydrogen was another element, so the selection was easy, selection of central atom. But here, between oxygen and fluorine, oxygen is less electronegative, so you choose oxygen. What is the first thing you do? Complete the octet on the central atom, right? And then how many fluorines do you have? 2. Now, out of 20 valence electrons, you put 8 on oxygen. How many more electrons do you have left? 12 electrons. And you can only distribute them on these 2 fluorine atoms, right? So you have 2 fluorine atoms. So what is the share of each fluorine atom? 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, and 5, and 6. So go ahead and change the bonding electron pairs to single dashed lines to distinguish between bonding and non-bonding. That's it. Now, the next example is what if we have an ion like PO4? It's not a problem, just a small change. Phosphorus is in group 15, so there are 5 valence electrons plus how many oxygens? 4. Oxygen is in group 16, so times 6. Plus you have 3 extra electrons on top of the molecule. So plus 3. That's the difference between a neutral molecule and when you have an ion. So you have 24, 29, and 332 valence electrons. Between phosphorus and oxygen, phosphorus is less electronegative, so it would be your central atom. Complete its octet. Put all the oxygens around it. And minus 8, it would be 24. You have 4 oxygens, so share of each oxygen is 6, right? 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, and 6. Because it was an ion, put it in the bracket and show the negative charge outside. And finally, change the bonding electrons to single dash lines. And you can show the non-bonding electrons on each of the oxygens. And again, show it inside the bracket with the overall charge outside. Then, one more time. In each case, the total number of electrons that you show here must be equal to these valence electrons. Let's move on. When do we know how to form the double bond or triple bond? Because not all the molecules have single bonds, right? Sometimes we see the double and triple bonds. So, keep it in mind, never forget it. We always start by forming single bonds. We never assume there is a double or triple bond in a molecule. We always start with a single bond and we will form double or triple if we have to. So let's see how it works for carbon dioxide molecule. The same drill. Let's count the total number of valence electrons. For carbon is 4 plus 2 oxygens times 6. So we have 16 valence electrons, right? Between carbon and oxygen, carbon is less electronegative, so it would be your central atom. Complete its octet and put the oxygens. Now, out of 16, you put 8 electrons on carbon, right? So 8 electrons left divided by 2 oxygens, so the share of each oxygen is 4. Now, we said around each atom there must be 8 electrons according to octet rule. So this is correct for carbon, but each of these oxygens have only 6 electrons. So we have to provide the 8 electrons for them. Before anything else, let me change the bonding electron pairs to single dash lines. Okay, so 6 electrons. 6 electrons. Each of these oxygens need 2 electrons. Whenever the octet is not complete on an atom, you need to borrow an electron pair from central atom over the bond between central atom and the atom that needs the electrons. So borrowing the pair of electrons from central atom over the bond. And do the same thing for this bond. So you will end up having now if you count, all of these atoms will have a complete octet. 1, 2, 3, 4, 5, 6, 7, and 8 electrons for carbon. Don't forget each line represents 2 electrons. Oxygen 1, 2, 3, 4, 5, 6, 7, and 8. And this oxygen 1, 2, 3, 4, 5, 6, 7, and 8. That's how you form double bond. Let's form a triple bond. Count the valence electrons, 1 for hydrogen, plus 4 for carbon, plus 5 for nitrogen. I didn't put 1 for each of them because makes it simpler. So there are 10 valence electrons total, right? Now, which one would be central atom? Hydrogen can never be central atom. Between carbon and nitrogen, carbon is less electronegative. So let's complete its octet. Now put hydrogen and put nitrogen. How many more electrons left? We spent 8 of them on carbon, 2 more. Can we put them on hydrogen? No. So let's change these bonding electrons to single dashed lines. Now, hydrogen is happy with its 2 electrons. Carbon is happy with its 8 electrons. But nitrogen is not happy with 4 electrons, only 1, 2, 3, and 4. So what do? We borrow electrons. How many more does it need? 4. 2 from here, 2 from here, to form the triple bond. Let me put them again so you see them exist. So you will have HCN. That's how a triple bond forms. Again, start from single bonds. If you have to, form double and triple bonds. All right? The next thing is that we call it delocalized bonding or resonance structures. Sometimes we have a combination of single and double bonds, but it looks like double bonds move over the molecule. I'll show you how. Let's work on the Lewis structure of CO3, carbonate ion. 1 times 4 for carbon, plus 3 times 6 for oxygens, plus 2 extra for these 2 overall charge electrons. So we have 24 valence electrons, right? 4, 18, 22, 24, yes. Between carbon and oxygen, carbon is the central atom. So if you put the electrons, you will have minus 8, you will have 16 left. 16 is not divisible by 3, number of oxygens. So go ahead and complete the octet from one of them. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, and 4. We should have put 16 electrons on oxygens, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. Each of these have 8 electrons. But how about this oxygen? This oxygen has only 6 electrons. So what do? I borrow electrons from central atoms. So it will change to, I have to draw it a little bit smaller because I need the rest of the space. I hope it's visible to you guys. So this was an ion. We said we have to put it in the bracket, right? So, do you see any difference between these oxygens? No. Seems like you even, you could have started from completing the octet from any of these oxygens. But I started from here, you could have started from here or here. So double bond can form between any of these oxygens and carbon. So you can have oxygen. Let me just draw it again. I don't have that much space. I'm a little bit worried about it, but it's okay. And let me put it here finally. So this time we form double bond between the bottom oxygen and carbon. All right. Now, seems like this bond, this double bond is moving between carbon and each of these oxygens. So we show it with a two-sided arrow, and we call them resonance structures. So this double bond is delocalized. It does not have a specific location. That's why we call it delocalized bond. And then if you move the bond on the molecule, it looks like they are constantly changing to each other. So eventually you will see this molecule. If you look at it under microscope, you will have such a thing. Okay? So these are called resonance structures. Another thing you need to know is formal charge. What is formal charge? First of all, it's a hypothetical charge. It does not exist. You just count this formal charge to decide between the two resonance structures. Sometimes you come up with more than one possible resonance structure and you want to decide. So let's see how you approach that. There are different formulas for formal charge. This is my own version of modified formal charge. Formal charge is number of valence electrons in a free atom minus lines plus dots. This part I have modified it. Lines are bonding electrons and dots are non-bonding electrons. So let's work on these two examples to make it more clear. We want to decide between these two resonance structures for carbon dioxide molecules. So we need to calculate the formal charge. Let's calculate the formal charge on carbon first. Number of valence electrons in free atom is 4 minus. How many lines do you see around the carbon? I see 4. Do you see 4? Plus, how many dots? I don't see any dots. 0. So the formal charge on carbon here is 0. These oxygens are both the same, right? So let's calculate the formal charge for one of them. That will be the same for the other one. So number of valence electrons in free oxygen is 6 because it belongs to group 16 minus. Lines around each oxygen is 2 plus how many dots? 1, 2, 3, and 4. So total would be 0. So formal charges for both carbon and oxygen on this molecule are 0. Let's work on this one. On carbon, you have 4 minus. Again, 4 lines plus 0 dots. So it's going to be 0. Let's call this oxygen 1. Let's call this oxygen 2. So oxygen 1 is 6 minus how many lines? 1 plus 1, 2, 3, 4, 5, and 6. So it's going to be negative 1 charge. And for oxygen 2, we have 6 minus 3 plus 2. So positive 1 charge here. The rule, how to decide. There are 3 rules for determining the formal charge, the best formal charge. You can use 2 of them here. First, between the 2 structures with different formal charges, you will pick the structure with 0 formal charges on the atoms. So which one so far is the preferred structure? This one. And plus, if there is formal charge on a structure like here, the one which is preferred where the electronegative element does not have a positive charge. What did electronegativity mean? It means tendency of atoms to pull the electrons. So oxygen is considered an electronegative element because it's almost on the right side of the periodic table. So positive charge is not a good thing on it, although it's a hypothetical charge. But that's another reason that you reject this structure. So first, 0 formal charges on the atoms, and then this positive charge here is not a good thing. In the next video, I will finish this chapter by exceptions on the octet and how to calculate the bond energies. You see?